So we began with the Hodgson-Huxley model, right, and then which shows you how to produce action potentials. From that, we went to more complicated models, into biophysical models. So we have seen dendritic processing, axon processing, synaptic transmission, all that. Now let us start stepping down and start looking at more simpler models, simplified models, simplified neuron models. Now, Hodgson-Huxley model is a 4-variable model, right? You have uh, because you have 4 variables: voltage, M, N, and H, right? The 3 gating variables. Whereas in the biophysical modeling, the number of variables is unlimited, right? As you add more, each compartment will have some variables, at least one voltage variable and some current variables. As you add more and more compartments, you will get more and more variables, and it is not uncommon to have a few hundred compartments in a single neuron model. And I'm known dopamine cell models having about 500 compartments. So that kind of thing is quite common. So in biophysical modeling, the number of variables can be very high even at a single cell level. So if your single cell model is going to be so complicated, obviously it will be very hard to model networks, especially large networks, considering that our target is to model the entire brain, which is a network of 100 billion neurons. So we need to somehow draw a line and come up with simplified neuron models. So for that, so the simplification, so we will go from Hodgson-Huxley model, the 4-variable model, to other neuron models, which are typically 2-variable models, because there is a very rich class of neuron models which interest in dynamics, which can be cast in terms of 2 variables. So, and one of the key properties of such 2-variable systems is limit cycles, right? So before going into these 2-variable models, Fujii Nagumo and Maurice Descartes and all that, let us go back and review a little bit about our limit cycle, the math underlying limit cycles. We look at a slightly new topic in limit cycles. So let us get back to our math preliminaries and learn a little bit more about limit cycles, and then we'll get back to our discussion of simplified neuron models. So coming to limit cycle discussion, we began with the definition of limit cycles. There are 3 kinds: stable, unstable, and half-stable limit cycles. Okay, and we also said that there is an important difference between the simple harmonic oscillator and limit cycle. In simple harmonic oscillator are what is called a center, right, in the classification of fixed points. It is periodic, but the amplitude depends on initial condition, whereas in the case of a limit cycle, amplitude is fixed irrespective of the initial condition. It has all these properties, so we have seen that. And we haven't derived any theorems, but we said we just gave 2 things. One is we gave this special system called the Half Oscillator, where we have seen that it has a limit cycle, which has where the unit circle is the limit cycle. So no matter where you start from in the plane, this system goes to the unit circle and keeps going around that. If you start from inside circle, it will expand and go to unit circle. If you start from outside, it will contract and again merge with the unit circle. Next, we saw this more general class of systems called the Leonard systems, where we just stated that if the equations have this form, what you see in this on the slide, where the f and g have all satisfy all these conditions, then again you have limit cycles, and we have seen the example of Van der Pol equation or Van der Pol oscillator, and we have shown that the Van der Pol oscillator equation satisfies the conditions of Leonard theorem, and it shows limit cycle. So we have come to this point. Now let us see the Poincare-Bendiction theorem, right, which is the third result we'll describe in our discussion of limit cycles. And this theorem tells you some condition or some conditions under which system will have limit cycles. So first of all, we need to note that when there is a limit cycle, and we are talking about only 2-dimensional 2D systems in all this discussion, there can be limit cycles in n-dimensional systems also, but they're very hard to analyze. There's a lot of theory of limit cycles in 2 dimensions, so we'll only stick to the 2-dimension theory. So first of all, when there's a limit cycle in 2 dimensions, note that no flow can flow outside right, go out of limit cycle. So if you start from inside limit cycle, I won't be able to go out like this, because that will contradict a very basic property. So basically, you have two equations. Sorry, x dot is equal to f of x comma y dot is equal to g of x comma y. So this is our system. So if you assume that it is possible to, in one case, one point, it's possible to go out of limit cycle, that will be a contradiction, because, so look at this point where this arrow is intersecting the limit cycle. At that arrow, if this is the limit cycle, then I should be going like that or like that, right? Whereas if we are saying that at that arrow, I'm not able to cross the limit cycle. So for the same x and y, I'm able to go in multiple directions. That's not possible, because given x and y, my x dot and y dot, which define the direction, is fixed, right? From the same point, I cannot go in three different directions or two different directions. So it's automatically a contradiction. So you will never be able to go out of the limit cycle. So this is a basic insight, all right, into the property of a limit cycle, which will let us understand or define this kind of a theorem. So based on that basic property of a limit cycle, this theorem says that if so here we are looking at more vector representation. X here is two-dimensional, and f of x is just a combination of both this small f and small g. Okay, so if you have a system like that, then and so I also assume that these two functions f and g are continuously differentiable. What that means is they have derivative everywhere, and the derivative is continuous. So that is a condition. If that is the case, then uh, imagine there exists a region R, right, which is a closed bounded subset of the plane. So within the plane, there's a region R, which doesn't have any fixed points, and also assume that there exists a trajectory C that is confined in R. That is, confined means, what does this mean? If it starts in R, it stays in R forever. So that kind of thing is quite conceivable, because we know that in a limit cycle, once you are inside a limit cycle, you will never be able to get out of it. So you can think of a trajectory which is confined to that limit cycle. So it's possible to come up with some region R, right, if there's a limit cycle somewhere around, right, where once you start from inside that region, you'll never be able to go out. So if these two are given, there is an R which is a region R, which is a subset of the plane, and then there are no fixed points in it. And also this, let's also assume that there is a trajectory C, which is confined in R. That is, once you start within R, you'll never be able to go outside R. If these two conditions are satisfied, then that trajectory C has to be a closed orbit, which means a limit cycle. Okay, so that's what the theorem says. I'll give an intuitive description of the theorem and how it can be applied. So first of all, one of the conditions is that this region should be a closed bound subset of the plane, and it's devoid of any fixed points. There should not be any fixed points. But there's a small problem here, because there's another theory called index theory, which is a theory from dynamical systems, where there's a theorem that says that any closed orbit must enclose one or more fixed points. So if I have a closed orbit, in this case is the limit cycle, there has to be some fixed point inside, right? You cannot avoid it. Okay, so if that is the case, then how can you have, so if I take a region R, and if I say that it doesn't you cannot go out of the region R, and if I say that there are no I won't be able to say that there are no fixed points here, because from index theory we know that if there's a closed orbit, then you should have limits, you should have fixed points. And how do I choose my region R, right? So there's a small contradiction here. So for that, what people normally do is choose a ring-like annular region. So because there's a limit cycle, I won't be able to go out, right? And but since there are the fixed points inside, I'll choose a region which is like that. Okay, maybe I should have chosen a different color. So I'll choose a region R, which is more like an annulus. So look at this whole region between the two red loops, right? It's an annular region. And if you can show that so this region doesn't have any fixed point because whatever fixed points are there inside the limit cycle, right? I will enclose them with a loop, and now I'll draw another loop outside the limit cycle, and I'll define my region R like this annulus. Okay, so in this picture, I'm just showing one fixed point inside, and I have this gray zone, right, is the annulus, and that's my region R. And I need to show that no orbit that starts inside this region R will be able to get out. If that is the case, if I can show that, then right, I don't have to prove directly that there is this limit cycle which is a closed orbit. The theorem will assure you that. All that I have to show is there is annulus R from which I won't be able to get out. That is, I need to show that I can't go out of this from the outer orbit. Similarly, I can't go out of this even in the inner orbit. Okay, so that is not very hard to show. You just have to have some understanding of the vector field, how the arrows are oriented. If I can show that, then theorem assures that there's a limit cycle. Of course, the theorem doesn't tell you where that limit cycle is. It just says it exists, like typically like lots of mathematical theorems. It's an existence theorem. So basically, this is the region R, then the gray zone. In it, all that you have to show is all the flows, right? The flows on the outer border of the annulus are pointed inwards, and flows on the inner border of the annulus are pointed outwards. If I can show that, I'm done. So how do you show that, right? Because to show that, it appears that I'll have to calculate, because my equations will tell me, right, x dot is equal to f of x comma y, y dot is equal to g of x comma y. At given x comma y, my equation tells me this equation, let me call this v, vector v is equal to x dot y dot. So this is v. Okay, so the given a point xy, I can find out what this vector v is. But then, does it require that I'll have to calculate this vector at every point in the plane, and and only then I can determine whether on this outer border I flow is inward, inner border flow is outwards. Then it will become computationally very heavy, right? Is there a simpler way than exhaustively calculating the flow values, flow vector, right, at every point in the plane? Right? The answer is yes, you don't have to calculate at every point in the plane. There are some simple hacks by which you can find out the flow pattern. Let's take a small example, a small linear system which can easily be computed, and you can find the flow pattern. And we'll use same kind of tricks later on to understand the flow pattern in more complicated nonlinear systems. So equations here are dx by dt is equal to x minus y, dy by dt is equal to x plus y. So now how do you understand the flow here? So just like in case of phase plane, I draw the null planes. What is the null plane? Null plane is where so you have x null plane, right, where x dot is equal to 0 is equal to x minus y. Then you have y null plane, where y dot is equal to 0 is equal to x plus y. So null planes are x minus y is equal to 0, x plus y equal to 0. X minus y equal to 0 is this. This is the x null plane. X plus y is equal to 0 is this. This is the y null plane. Okay, so now let us try to understand the flow right around these null planes. So on the null plane, so if you look at the x null plane, right, x dot is equal to 0. So only y dot is non-zero, right? So this is what we learn about the x null plane. Similarly, on the y null plane, y dot is 0, so x dot is non-zero. So that is, let's keep that aside. Now, if you look at x null plane, x minus y is equal to 0. So if you go above the x null plane, that means on the x null plane, x minus y is equal to 0. So if you increase y above this, then this quantity becomes negative. So which means x dot becomes negative. So if I go above this line, x dot is negative. So we'll have written this down here. X dot is negative. So x dot is negative above this line. Now you see that the two lines intersect at a point and form four quadrants. The four quadrants are not identical, but the two lines divide the whole plane into four regions. So one is this region, okay, another is this region, and this region. Kind of like four sectors. So when you say above the external plane, that includes two of these sectors, this one and this one. And you see that in both these sectors, x dot is negative, because in both of them, x minus y is negative. So x dot is negative here, x dot is negative here. So contrarily, when you go to below the external plane, x minus y, then so if you below means y is less, that you're reducing y. Okay, so that means x minus y becomes positive. So if x dot is positive, if x dot is positive in this sector, and x dot is positive in this sector also, so x dot is positive. So like that, without doing any detailed computations of this thing, just by looking at these broad patterns, and just by using the information that on the external plane x dot is 0, right? Then that means what happens when you go to one side. So we are just looking at the signs of the quantities. We are not doing detailed computations. So now let us look at the y-null plane. Y-null plane is given by x plus y is equal to 0, right? So if you increase y, if you look at above this null plane, that's increased y, that quantity becomes more positive. So therefore above this y dot is 0, and above this here also y dot is 0. So above this means this sector and this sector. So y dot is 0 here and y dot is 0 here. Now contrarily, if you go to below the y-null plane, y dot should be negative. So y dot is negative here, this sector, y dot is negative here, this sector. So without doing any detailed computations, but just by simple approximate arguments, you are able to find out the flow pattern over the entire vector field in the two dimensions. What is the flow pattern like? If I look at this quadrant on the top, x dot is negative, y dot is positive. That means the arrow is turned to the left, x dot is negative. Arrow is turned upward slightly, y dot is positive. Okay. Similarly, if you go to the left sector, it says x dot is negative, y dot is negative. That means arrow is turned to the left because x dot is negative. Arrow is turned downwards because y dot is negative. Similarly, in this quadrant or this sector, x dot is positive, y dot is negative. So the arrow is turned to the right and to the downwards a little bit. Then in the right sector, x dot is positive, y dot is positive. So therefore, the arrow is turned to the right and turned upwards. And in this particular picture, you can easily see that the flow has some kind of a circulating current, kind of circulating pattern. Because the arrows seem to chase each other, forming some kind of a circulating pattern. And you can easily imagine there must be some kind of a focus, right, or a center or something like that, some kind of a spiral, right, or a center or something like that, because of this classic circulating kind of a pattern. Had it been a stable node or something, all the arrows will be simply pointing towards this fixed point, because the origin is a fixed point here, right? Because at x and y is 0, the x dot is 0 and y dot is 0. So this gives an intuitive understanding of how you can calculate the flow patterns by using some loose arguments. So now let us try to apply the condition or verify the condition of the Pancreatic Bendiction theorem, and show that there are limit cycles in particular example. This example is given in Stogads, right? You can look at that. So the two equations here are, these are nonlinear equations. X dot is equal to minus x plus ay plus x squared y. Y dot is equal to b minus ay minus x squared y. So if you take the x null line, x dot is equal to 0, you have y equal to x by a plus x square. And if you look at the y null line, y dot is equal to 0, you have y is equal to b by, just solve this, you get y equal to b by a plus x square. If you plot, now also this is actually a model of glycolysis, and x and y are some chemical concentrations. So x and y are positive. So x is positive, y is also positive. There's some chemical concentrations. Right. So let us look at the first expression. X dot is equal to minus x plus always. I can take a plus x square out, and I have uh, okay. So the null line is given by y minus x by a plus x square, right? So if so, this is equal to 0. So if y is above this null line, that means y is increased further. Then you can see that x dot becomes positive. Similarly, if y is below this null line, you can see that x dot becomes negative. Okay, so take the second null line. Y dot is equal to b minus this. So this will be this quantity. Okay. So y is above the y null line. That means y is increased further. So this quantity becomes negative, and y is below the y null line. Y dot is negative, is positive. So let us depict this in the curves. So what are the two null lines are given by y is equal to x by a plus x square is x null line. So x by a plus x square is this, and so this is the x null line. Now you see that at x equal to 0 it goes to 0, x equal to infinity again it goes to 0, right? So in between it goes to a maximum, right? So this is how the x null line is. So similarly, if you look at the y null line, y null line is given by b by a plus x square, and a and b are positive. So this starts from some value. So by this value is b by a, and simply at x equal to infinity it goes to 0, so it goes down. So you see that these two intersect at some point, and you can also show when and what condition they intersect and what is the intersection point. You can easily calculate. Okay, so now if you look at these results, for y above x null line x dot is positive, y below x null line x dot is negative. So let us show that here. Y above x null line x dot is positive, so that is positive. So here also you can see that the two null lines, they are not straight lines, but they divide the entire plane into 4 regions, right? So this open-ended region, which is infinite, right, is one region. This is the other region which is also open-ended and infinite in nature. This is also open-ended and infinite. Okay, and the fourth one is finite. This one. So this is how the two null lines divide the entire first quadrant of the plane, because that's the only valid region here. The entire first quadrant of the plane is divided into 4 regions. So when you say above the x null line, that involves 2 regions, and in both these regions, x dot is positive, x dot is positive. Okay, so therefore, contrarily, when you go to below the x null line, x dot has to be negative, and x dot has to be negative. So in these 2 regions. Okay, so now let us look at the y null line. So you have seen that in case of y null line, if you go above the y null line, y dot is negative, below y dot is positive. So this is the y null line. So above that means 2 regions. This is one region, y dot is negative. This is a second region, y dot is negative again. So contrarily, there are 2 regions below the y null line. That is this region. So y dot is positive here, below y dot is positive. So with these simple arguments, we are able to get the flow pattern qualitatively over the entire region of interest, or entire in the phase plane, right, which is the first quadrant. So what have we learned? In this region, the flow is downwards and rightwards. In this region, flow is downwards and leftwards. This region, flow is upwards and leftwards. This is region, flow is upwards and rightwards. Okay, and also note that the flow on the null planes is interesting. Flow on the on the y null plane will have only horizontal direction. In this case, it's rightwards. Flow on the x null plane will have only vertical direction because x dot is 0. In this case, it is downwards. Similarly, here it is leftwards, here it is upwards. So you can easily see that you can, like a bunch of sharks going around prey, right? Here you see all the arrows showing a nice circulating pattern. You can kind of sense that there is a limit cycle sitting somewhere here. Okay, so that's not enough. These loose arguments are not enough. We need to actually show that there is a outer border where flow is pointed inwards, and there's inner border where flow is pointed outwards. If you can show that, then you can invoke the Pancreatic-Bendiction theorem, right, and show that there exists a limit cycle. So how do we show that? Let us take this dashed line as outer border, right? So this dashed line has many segments. There's a vertical, there's a part of the border is the y-axis, part of the border is x-axis. Then in addition, there are 3 segments: this horizontal stretch here, this vertical stretch here, and then this oblique stretch here. So what we want to show, it is very carefully chosen contour. What we want to show is that over this entire border, the flow is pointed inwards. So how do we show that? First, let us look at the y-axis part. And we have already shown that in this part, flow is pointed upwards and rightwards. So since it is rightwards on the border also, right flow is pointed inwards on the border. So that's easy. So similarly, we have shown here that in this bottom segment, right, flow is leftwards and upwards. Therefore, on this bottom border also, flow is upwards, which means it's inwards. By similar arguments, you can also show that in this segment, flow is leftwards and downwards. So therefore, on this border also flow is leftwards, so flow is inwards. Now take this small stretch. So you've taken this small stretch. Okay, up to the point B and B by A. So you see that in the y-axis, this value is B by A. Right, in the x-axis, I want to go up to the point B, and that point happens to be exactly the coordinate of this intersection point. So you can easily show that at that point, up to this point, right, the flow is downwards or inwards, because so we have seen that in this entire segment or region, flow is downwards and rightwards. Therefore, in this small stretch also, right, flow is downwards, which means it is inwards. The problem comes in determining the flow direction along this slope, because we know that in this entire segment, flow is downwards and rightwards. But is the slope of the arrow greater than -1? Because the slope of this line is -1. The flow will be inwards into the line only if we are able to show that the slope of the line is greater than -1 in magnitude, right, or less than -1 in actual value. So that's indeed the case, because if you calculate x dot minus of minus y dot, which is x dot plus y dot, and that can be shown to be, if you just plug in, this is x dot value, this is y dot value. If you calculate this, you get b minus x. So in this stretch, my x is greater than b, right? Because up to this point, we have taken b, and beyond that, x is greater than b. So if x is greater than b, then this quantity is negative. So this quantity is negative. So which means x dot minus of minus y is, so minus of minus y dot is negative. So x dot is less than minus y dot. Okay, so which means uh, so y dot is negative, right? Because it's pointed downwards. Now minus y dot is therefore positive in magnitude. So from this we know that mod x dot is less than mod y dot, or mod y dot by x dot is greater than 1, right? So which means the slope is greater than 1 in magnitude. Slope is, the flow is pointing downwards, but slope is greater than 1 in magnitude, so which is what we wanted to show. So you can, so now you are assured that flow is inwards on this part of the contour also. So if you look at this dashed contour, if we are able to show that the flow is inwards on in all segments of the contour. This is a fairly elaborate argument, but we have shown that. Now we need to decide on inner contour and show that on the inner contour the flow is outside or outwards, going inside into this gray zone. So that's very simple because the inner contour is chosen always based on the fixed points. And usually if you want a limit cycle, it will have an unstable focus inside somewhere. That's a general thumb rule. So this point is a fixed point, obviously, right? Because it's an intersection point of the two null planes. Now we need to show. So we'll just pick a small region, epsilon circle around the fixed point. All that we have to show for flow to be outwards in this circle is that this point must be unstable. If we show that, obviously the flow has to be outwards. So what is a fixed point here? So it is these two are equal, right? That is when the y equation equal to y null plane is equal to x null plane. Then the answer is x equal to b and y equal to b by a plus b square. So at this point, now we want to find out is the point unstable or stable. So as usual, find out the Jacobian. Jacobian is given by this, right? And if you apply the fixed point here, right, and do the stability analysis, we can show that this is a tau, okay, and delta is equal to a plus b square. That is positive because a and b are positive. Trace is this. So this fixed point is unstable when tau is positive and stable for tau is negative. We want it to be unstable. So tau is 0 when this is true, this equation is true, and this is the relation between a and b. Okay, so which means in the AB space, because AB are the two parameters of the system. In the AB space, right, this border is where, this is the border where tau is 0. So inside this region, in the gray zone, tau is negative, outside tau is positive. So therefore this table is, this is other way around. This is, the fixed point is stable, which causes a stable limit cycle. So if the fixed point is unstable, right here, then that will give you a stable limit cycle. So this is the condition under which we have a unstable focus, right? This point is unstable, and then this circle, right, will give you all the flow going outwards. So then we would have shown that these two set of contours and the region which encloses them is like our region R. Okay, this region R, now we have shown that any contour which starts inside this will be confined to this region R. All right, now, and our system is also defined over a bounded region, and there are no fixed points inside this region because whatever fixed point is there, we have cut it off. We have omitted it from this region R. Therefore, the Pancreatic Bendiction theorem says there is a closed loop inside this. There is a limit cycle inside this. Okay, so we can just say that there's a limit cycle inside this. If you simulate it, you can see the limit cycle going around, right, somewhere inside the gray region. So it's a fairly elaborate procedure, and also there is no standard procedure for finding the region R. It depends upon your intuitive understanding of the system and so on. So we won't be using this technique in detail later on in the course. but we'll just use these arguments about how to find the flow pattern over the entire phase plane, simply in using qualitative arguments, not by actually computing the vector field at every point. So we'll use these arguments later on when we discuss simplified neuron models, right? So let us stop here. So there is one more way in which you can show limit cycles, right? That is by bifurcation, particularly a bifurcation called half bifurcation. So we'll look at that in the next class on Friday. And after that, we'll start this discussion of simplified neuron models. Okay, and thank you. Any questions?